Thank you all for coming to my presentation. The topic of my talk is virtual environments and dependency management in Python. So as you can see, it's more a Python general presentation. It's focused on tools that you can use to, first of all, manage virtual environments and Python installations, and the second of all, how to manage dependencies of your project, of your Python project. My name is Piotr Grzesik, and it stopped working for a second. Okay, so what I do on my day-to-day job, I'm a Python and blockchain developer in Pragmatic Coders, and in addition to that, I'm also one of the organizers of a Krakow Python user group called PyConic. And what I will be talking about is I want to answer 2 questions. How you can manage multiple Python versions on your computer, how to manage virtual environments and what they are useful for, and how you can manage project dependencies so you can achieve reputable environments. Oh, I believe that's not working as it should. So let's switch a little bit. Sorry about that. Sorry for that. But I believe that internet is not working properly. Nie działa nic. O, teraz dopiero zaczęło działać z powrotem. So let's try again. Oh, there it is. Okay, sorry for the technical problems. So I would like to answer 3 questions: how to manage multiple Python versions, how to manage virtual environments, and how to manage project dependencies. And for starters, probably since you're using Python, a lot of you already know pip. I just wanted to mention that it's a package installer that is recommended by Python Packaging Authority. It's distributed with Python from versions 2.7.9 and 3.4 and above. And by default, it uses packages installed from pypi.org. You can go to that site and search for the packages here. And how to use pip? It's actually quite straightforward. You have the command available pip install for installing packages. You can also specify the minimal version, like in the second example. You can specify the exact version of the package that you want to use. And you can also use requirements.txt format file for installing multiple dependencies at once with the -r flag. For uninstalling, we have pip uninstall package command. Two other useful commands are pip list and pip freeze. Both of those are used for listing installed packages. There's a small difference between them. Pip list lists all the packages that are installed. It includes also pip, since it's also a Python package. It also includes setup tools, for example. But it has a really useful flag, which is -- outdated. And with that flag, you can check for outdated packages in your environment. With pip freeze, you can produce a list of all installed packages, excluding pip and setup tools, and you can use it to quickly produce the requirements.txt file. So let's try to answer the first question, which is how to manage multiple Python versions. And for that, we have the tool called pyenv. So if you're, for example, working on multiple projects with multiple Python versions, you can use that. In addition to traditional CPython, you can also install other interpreters, for example, PyPy or JPython or IronPython. If you're familiar with Node.js or Ruby ecosystem, it's really similar to tools like NVM and RVM. What might be disqualifying for some of you, it's not working on Windows. I looked but failed to find the working solution for Windows, but I will also mention other tool that is able to manage Python versions on Windows. And how it works in a little bit of magical way. So what it does, it inserts pyenv shim's directory at the beginning of your search path. So when executable is searched for, it always will find shim with the executable, and the shim is a small file, small program that that passes the command to the correct pyenv. So for example, if you want to invoke the command pip, the path will be searched for the executable named pip. It will find the pyenv shim named pip, and it will pass it to the correct Python version. And how the correct version is chosen? First, it checks for the environment variable called pyenv version. We can set that environment with the command pyenv shell. If that's not found, it checks if a file .python version exists in current directory. You can use the command pyenv local for that, for creating that file. You can also create that file by hand if you'd like. If that's not found, it tries to find this .python version file in the parent directory. It searches up to the root of your file system. And if that's not found, it uses the default, which is stored in your home directory, .pyenv/version file. And you can use the command pyenv global to actually set that. I also want to mention the pyenv update plugin. It only does one thing. It provides the ability to actually update your pyenv installation. It not only updates pyenv, but also all plugins. So basically what it does, it updates available Python versions. So if you're using pyenv and you're not updating it for half a year, then you will be missing the latest releases of Python or other distributions of Python, for example, JPython. And how to use it? As I said, we can install different versions of Python interpreter with it. For example, you can install Python 3.6.2. What's interesting, it can also install, for example, Anaconda. Probably some of you are using Anaconda. It also has it available. For listing all available Python interpreters, you have command pyenv versions. And for uninstalling, you just type pyenv uninstall with the proper name or proper version. And as I mentioned before, you have the command pyenv shell, pyenv local, and pyenv global for setting current Python interpreter. And you can check which one is used with the pyenv version command. So. So now that we know how we can manage multiple Python versions, we can move on to virtual environments. So it's a different type of separation. On pyenv level, we're separating different versions of Python on our system. With virtual environments, we're actually separating environments with the same version of Python. So what we get is isolated and independent environments. So we can be sure that we can use, for example, library in 2 different versions if you want to test it, or if you want to be sure that we won't break our Python, our system Python installation. And yeah, it basically allows testing and using third-party libraries without worries, and to isolate your project from the other part of the system. And since it's very popular in Python community, it became a part of the standard library, starting from Python 3.3. And how virtualenv works? There's also a little bit of magic to it. First of all, there are two parts. For using it, we're using the activate command, and essentially what it does, it just inserts a path to the binary of Python at the beginning of path, so the proper Python will be used when you're trying to invoke it, for example, from the command line. And the second part, how it actually resolves modules that are installed. Python uses something called sys.path. You can import this module and check what's in there. It contains a list of search paths for modules during imports. And this sys.path is populated by a file called site.py. So what the guys from virtualenv did is to modify that site.py, so it will point and so it will populate sys.path with the paths to the virtual environment. And not to replicate the standard library, they also included the orig prefix txt, which allows to include standard library from the Python installation from which the virtualenv was created. And a little different approach was used by guys that implemented it in standard library. They actually used the file called pyenv.cfg. And if there is this file available, then the Python interpreter knows that it's running in the virtual environment. So it can create two prefixes, sys.prefix, which is a prefix pointing to the virtualenv installation, and the sys.base prefix, which is pointing to the original one. So it can include the standard library from the original one. And in both cases, the packages are installed to path2env/lib/python with number version and /site packages. You can inspect them here. And you can see how the pyenv.cfg file looks. Home just points to the location of the Python binary from which the virtualenv was created. And the include system site packages, we can set it to true if we want to use the packages installed on the system Python, and also the version. So how we can use it? It's quite straightforward. If we're on Python lower than 3.3, we need to install it. For example, with pip. And after installing it, we have the command virtualenv available to us. We just say where we want to create our virtualenv. With Python 3.3 and higher, we have two options. One is already deprecated, so I'm not recommending to use it, but it's available, so it's good to know. It's called pyenv, and we just point the path where we want it to be created. But the recommended option is to use python -m -venv and provide the path. And we can activate it with sourcing the activate file, or and after that we can just type the activate command to deactivate the virtualenv. So, but to simplify things, there is a plugin which is called pyenv virtualenv, which integrates virtualenv with the pyenv, so we can create virtualenv from the pyenv. It also has supports for managing conda environments that I will be mentioning in a bit, and it works with the virtualenv installed from pip as well as the one that is a part of the standard library. The commands to use it are quite straightforward as well. We just type pyenv virtualenv. We can provide the version and the name of the virtualenv. If we omit the version, it will use the currently used one. With pyenv virtualenv, we can list all of existing envs, and for working, we also have activate and deactivate. But we need to use pyenv. We need to use pyenv version with pyenv activate and pyenv deactivate. And for removing, we have pyenv virtualenv -delete command. So other tool that combines all of those, so environments, managing Python versions, and installing packages, is conda. What's important is it's multi-platform, so you can use it on Windows, unlike the pyenv that I mentioned before. It also supports pip for installing packages inside environments. And what's really important about conda is that it installs binary packages So there is no need to compile, and there is no problems with installation. Like, for example, you're missing compiler, and you have problems with it. And thanks to the fact that it installs binary packages, it's also possible to install packages that are written in other languages. For example, it treats Python as every other package. So you can also install, for example, packages from Fortran or binaries from C. And it comes with Anaconda and Miniconda distributions. And how we can create environments with it? We have the command conda create. We can provide the name. We can provide the list of packages that we want to install in our environment, for example, Keras. We can also specify the Python version. We can also create a clone of existing environment with the --clone --clone flag to our command. For listing environments, we have conda info --envs, or the newer version, which is conda env list. And for working with them, we have similar commands as for virtualenv and pyenv virtualenv, activate and deactivate. You need to prepend the source if you're on macOS or Linux. And for removing, we have conda remove. We provide the name of the environment and add the flag --all, so it will remove the whole environment. And installing packages is similar to pip. However, as you can see, there is only one equal sign between name of the package and the version. And you can also, by default, it installs in currently activated environment. But you also can provide a name explicitly, so you can be sure that it's installed in the proper one. And for uninstalling, you have the conda remove, and similar to installing, you can also remove from the specified environment. And for inspecting installed packages, we have the conda list command. And about dependency management. So what can we get from dependency management? So for example, you start the project, you just have a simple script, you're pip installing everything in your virtual environment. But later, for example, you want to share it with someone. You want to share it with a colleague. You push it to GitHub, other person clones it and tries to run it, and it doesn't work because it's missing libraries. So the first thing that we get from dependency management is that we have a list of external libraries that our project actually needs to run. It's very often in a simple form of the requirements.txt file. We can go further with that, and we can provide a few requirements.txt files. So we can provide, for example, logical separation of dependencies. For example, we can create a separate list for testing, for development environment, and for production environment. We can also provide a simpler list for humans to read, and also we can provide a list for machines which have all dependencies with specified versions locked. So we are able to actually create. So we are actually able to produce environments that are exact the same as on our machine. So we don't have a problem that it's working on my computer, but if you do it right, then it's really easy to reproduce on production machine or other user computer. So to start with it, we have the simple tool, which is called piprex. It only does one thing. It inspects your whole project for imports, and it creates a requirements.txt file with all the packages that you actually imported in your file. That has a big advantage over the simple pip freeze redirect to requirements.txt, because you maybe forgot that you installed other packages. For example, you installed IPython or something else, and you don't need it to end up here. So it will just include the packages that your project is actually using. Important, it only includes those packages that are imported in your project. So the dependencies of those packages are not included here. But if you also want to include them, which is a really good idea, not so good idea if you're writing libraries, because users of your libraries may have problem. But if you're creating an application or some script, then it's good idea to pin all your dependencies, so provide all specific versions, not only for dependency that your project uses, but also packages needed by those dependencies. And for that, we can use a tool called piptools, which have two commands. It's essentially two tools. It's pipcompile and pipsync. And it has a notion of having two separate lists. One is for humans to read, and one is only for machines, which is not supposed to be edited by human. And how it works. For example, we have a simple project that uses two packages called, for example, Flask and Request. Those are two of the most common and popular packages in the Python ecosystem. And we save it in a requirements.in file. And with pipcompile, we can produce our pinned requirements.txt file, which will be a list of dependencies for machines. The first one is just for humans, just simple top-level dependencies. And at the end, after the pipcompile, as we can see, the list is quite bigger. All packages have specified versions, and in addition to Flask and requests, we can see that there is more. We can inspect in the comments created by pipcompile which package was installed, like what was the source for this package, why was it installed. For example, we can see that Jinja 2 was installed because of Flask. And we can also use it to upgrade later specific packages, because the requirements.txt is not supposed to be edited by human. So if you want to update it, you again pipcompile the requirements.in file. We can also use -- generate hashes flag, which will, in addition to pinning your versions of dependencies, in addition will also create hashes for the packages. So if someone is tampering with the package on the PyPI, for example, and there is the version number is the same, but the package is different, the hashes won't match, and it won't be installed. And to sync a current environment with requirements.txt file, you can use the command called pipsync. It will uninstall all packages that are not specified in the requirements.txt and install all needed. So you have a clean environment with only packages that actually your application needs. And I also wanted to mention a new standard that is coming. Right now it's only experimental, but there is a specification called pipfile, which is called requirements.txt 2.0. It's the proposition of a new standard, and this project is supported by PyPI. It's supposed to replace the requirements.txt with not only one file, but two files, which will be similar to the example from piptools. We will have a pipfile and pipfile.log. When with pipfile being like the list for humans, which will only contain top-level dependencies, and the pipfile.log will contain all pinned dependencies with hashes and the source from which the packages should be installed. And they use the TOML syntax instead of just simple requirements.txt format. And that's an example of a simple pip file. What's neat about it is that it contains additional section called dev packages, which is a good place to keep packages that are not needed on production servers. So, for example, PyTest for testing, or IPython for playing with the code, or something like that. So that's cool that we have one file, but because if we want to use it with pipcompile, we need to have separate, for example, dev-requirements.in file for that. We also have the Python version and the source for the packages. And I just wanted to show the pipfile.log. It's not the whole file because it's much bigger, but as you can see, it contains at the end of the slide, there is one of the packages. We have the pinned version, we have the hashes, and There's only one project right now that actually uses this new format, which is called pyenv. It's recommended to use by Python Packaging Authority. So I believe that in the coming future, the pip file format will be much more common and much more widespread. What it is essentially a mixture of pip file, and virtualenv. So a little bit similar to conda. What it does, it automatically creates virtualenv for you, so you don't need to worry. If you install something, it will create a virtualenv for you if it doesn't exist yet. It automatically also adds and removes dependencies from pip file during installation and uninstallation. If you're using the pip tools, you need to manually add everything to your requirements.in file. But with pyenv, if your pyenv installs something, it will automatically update your pip file. And it also creates the pip file log file. It can install dependencies from that file. The pip file log, also I didn't mention, it's not supposed to be edited by human, similar to the requirements.txt from the previous example. And it by default uses hashes for packages verification. And to manage Python versions, it recently added integration with pyenv, so you can have everything. By using pyenv and pyenv, you have management of versions, management of your dependencies, and virtual environments. And how to use it? You can manually create a new project with specifying Python version. If you don't do that, during pyenv install, if the project doesn't exist, if your virtualenv doesn't exist, it will be created. If you pyenv install request, it will be added to the pip file. If you add the flag --dev, it will be added to the dev packages in pip file. And uninstalls the package and also removes it from the pip file. And for installing all dependencies, we have the pyenv install command. It will install all dependencies from your log file, excluding the dev packages. But if we add the --dev flag, it will install all dependencies. And for spawning a shell with virtualenv, we have pyenv shell command. It also has a few additional features. One of them is pyenv graph, which is useful for actually looking how the dependency graph or our project looks like. We have also pyenv check, which checks for security vulnerabilities of our installed packages. And we can also manually generate the new log file, so it will update the versions with the pyenv log command. So the summary. For installing packages, you have pip, conda, and pyenv. Pyenv uses pip underneath. For managing Python installation, you have two options, conda and pyenv, or you can manage them yourself. For environments, we have virtualenv, pyenv, and conda or pyenv. And for managing dependencies, pip tools and pyenv are the most common one. And my recommendation would be to use pyenv with pyenv. You have everything with that. Or if for some reason you want to be sure that all your binary packages are working, then you can go with conda. I have much more experience with pyenv, and it's working really great. And that's my recommendation for using. And thank you.
Thank you. Just a short question. Why don't you recommend working with conda? Because for me, it makes life much more easier because it takes care also about the binary stuff. And for example, with pip, sometimes you need to install some system dependencies, and it's a pain. So why not forget about all these other tools and just use conda?
Actually, conda is not officially supported by Python Packaging Authority or Python Software Foundation in any way. So that's why I'm recommending other tools that are recommended. And to be honest, I believe conda is only popular in data science communities and machine learning. It's not really used outside of that.
So anyone else? Thank you, Piotr.